And you are of course most welcome. This is Project Euler problem number 2. Each new term in the Fibonacci sequence is generated by adding the previous two terms. By starting with 1 and 2, the first 10 terms will be these. By considering the terms in the Fibonacci sequence whose values do not exceed 4 million, find the sum of the even valued terms. Now, the Fibonacci sequence appears all the time in mathematics, and naturally it appears all the time in Project Euler. So we need to get to grips with some of the interesting little quirks of the sequence, and I'm going to show you two of them today. First, we'll go through a basic brute force solution to this problem, which is fairly simple. We have a totalizer, which I'm going to set to 2, because we've already got the first two values, 1 and 2. So T1 is 1, and T2 is 2. Remember, the next term in the Fibonacci sequence is the sum of the previous two terms, so we're going to constantly update these two, the previous two terms, and then see if the latest term is even, and if it is, we add it to the total. So while T2 is less than 6, while T2 is less than that, we do T3, the next term in the Fibonacci sequence, which is the sum of the previous two terms. If T3 mod 2 is equal to 0, then total plus equals T3. Then we update the values, so T1 becomes the value for T2 and T2 becomes the value for T3. This all makes sense, I promise, and then right at the end we print total, and that produces the correct answer very quickly because the Fibonacci sequence gets very big very quickly. So this will do it in a very short space of time. The problem is I hate it. I hate it so very much because, well, not only because it's brute force, but because look at all these T1s and T2s and T3s. And there are probably other ways to do this, but yeah, I hate this. So let's get rid of that and never think of it again. Right. I'm going to discuss two very interesting properties of the Fibonacci sequence with you. Now, the first one is that you don't need to calculate all the terms in the Fibonacci sequence. You can get to any term by constantly getting the sum of the previous two terms. We don't need to do that. There is actually a formula that will allow you to find the nth term without having to loop through all the other terms. So it uses something called the golden ratio. So the golden ratio in mathematics is normally denoted with the Greek letter phi. In fact, yes, we'll move that down a bit. So phi is equal to 1 plus the square root of 5, which I shall represent as 5 to the power of 0.5, divided by 2. That is the golden ratio. And again, this is something that appears all the time in mathematics. So we use phi in the formula to find the nth Fibonacci term. So let's represent this as a function, def Fibonacci n. So all this function will do is take a number n, and then return the nth term in the Fibonacci sequence. So return, what are we returning? It's going to be phi to the power of n minus 1 minus phi to the power of n, and then it's all of this divided by the square root of 5. Now this will produce an irrational number because phi is going to be irrational. It has to be irrational because this is irrational, and we want it to return an integer. So what I'm going to do is I'm going to import the floor function. So from math import floor. So I want the floor of all this. I basically rounds all this down to the nearest integer. Why do you have a problem with that? Oh, it doesn't like I. Oh, that should be a 1. Silly me. There, that will do. Now, the second interesting property of the Fibonacci sequence is this. First term is 1, second term is 1, third term is 2, third term is 3, fourth term is 5, sixth term is 8, seventh term is 18, eighth term is 21, ninth term is 34. Now, what have you noticed? Did you notice that every third term, and only every third term, is even? So we don't need to cycle through all the Fibonacci sequence. We only need every third number. So n equals 3. And we shall start from there. So while Fibonacci n is less than 4 million. Is that 4 million? Yes. So while Fibonacci n is less than 4 million, we do need a total. Total equals 0. Then total plus equals Fibonacci n. Don't need to test if it's even because we know it will be. And then n plus equals 3. We print the total. And there we go, exactly the same answer. So, again, always look for a solution that is not brute force, and you'll have a much happier time, especially when you come to the problems after about 50. So, I will see you next time for problem number 3.